Hi everyone. My name is Sasha Zelanovic, and I'm a principal product marketing manager here at Red Hat. We're really excited to have you for our vLLM office hours today. Just 24 hours ago, we decided that we can't miss out on all the DeepSeek fun that's happening all over the world. So we changed the office hours topic from talking about vLLM V1, to actually DeepSeek. So I just really want to give a big round of applause, and I'll do it myself here, to the team that you see on the screen right here, who came together in the last 24 hours and really put this presentation together to drive this amazing discussion. So thank you guys so much. And one special shout out also to Lucas Wilkinson, right there in the right middle, for becoming the most recent vLLM committer. So congrats, Lucas, and thank you guys one more time. So Michael, if you can please go to the next slide.
Yep, thanks.
So just a few housekeeping items before we start. So we love making this an interactive session. So if you have any questions, if you have anything to say, comments, whatever that might be, feel free to raise your hand or just unmute yourself and start talking. You can also use the Zoom chat that seems to be popular with this audience to ask any questions. We have a big team here ready to answer any questions that you might have. Let's quickly just test out the Zoom chat like we usually do. And if you can just pull it up right now and type in where you're dialing in from, you can see all the flags from countries of people that were represented over the last 20 sessions. So we always love adding new flags. We did run a city analysis this morning. We didn't put a map here, but we have pretty wide coverage when you put cities on the map as well. It's pretty interesting. One thing that we learned is that Asia is definitely sleeping at this time. So maybe it will be time sometime soon to introduce multiple sessions each day. So let's see: India, California, Boston, Vancouver, Cincinnati, New York, Westford, Mass. Welcome. Hey, Max, Brazil, of course, San Diego, New Zealand. Colin, super nice to have you. I think you might be the furthest away from here, where we are in Boston. London, UK. So super nice to have you all guys. Welcome one more time. So this session is being recorded and live streamed right now, because I always forget to click that button. So we're actually being live streamed right now on X, LinkedIn, and on YouTube. If you have any follow-up questions, you can always ask him in the vLLM Discord and the developer Slack. Links are there, and Michael shared that deck with you guys, so you can go through all the links. And we will be emailing this recording to you probably on Monday. So feel free to respond that email as well, and we're happy to assist you. So Michael, with that, I'll pass it over to you.
Yeah, thanks a lot, Sasha. Hi, Michael again here. So we got lots of things to cover today. First we'll cover quickly AI Bricks, which is a new project joining the vLLM project. Then we'll cover vLLM 0.7.2 and 0.7.3, which have some new model support and a pretty cool transformers backend. And then, of course, a lot of optimizations for DeepSeek and V1, which have been top priorities for the team. Of course, we're going to be doing a deep dive into all the things that we're doing inside of vLLM to support DeepSeek well. And then, of course, kind of a summary of what things DeepSeek has been open sourcing in this week of open source, and how we're already integrating them in vLLM or planning to integrate them. We wanted to put a shout out to the next office hours, where we're going to cover the vLLM production stack project from Yihua at University of Chicago. That should be a good one. And of course, we're having our first East Coast vLLM meetup in 2 weeks on March 11th. So if you're near Boston, come and join. We're going to have a great party. So if you're not already familiar with vLLM, it's the de facto standard in open source model serving. It's an easy to use open source inference server, Apache 2.0. It's a pip install away or a Docker image away. And we try to make it very easy for you to use any open source model that comes out, and make it easy to deploy. Bundling in the state-of-the-art inference acceleration research and open source things like we're doing with DeepSeek, and giving you great performance on NVIDIA GPUs, but also having diverse hardware backend support, like for AMD, Intel, Google, Amazon, Huawei, many different hardware backends plug into vLLM. So it's the common software stack to deploy large language models. We don't just do text-only models. We also have support for multimodal and embeddings and reward modeling. So vLLM is being increasingly used in some of the RLHF workflows and post-training workflows, where a lot of inference or test time compute is needed. Um, yeah, we have lots of quantization support and inference optimizations like chunk prefill or advanced scheduling or multi-LoRa batching. And of course, application level features like tool and function calling and structured outputs. Many different types of parallelism, tensor parallelism, pipeline parallelism, now expert parallelism and data parallelism, which we should add here and we'll get into and explain a bit today. But that's the gist. And then, of course, most of us here are from Neural Magic and now Red Hat, and we are a top contributor to the project. We're working a lot on vLLM v1 and DeepSeek as well. Here are some of the things we've worked on in vLLM before, and generally we help enterprises make their vLLM deployments more successful and make sure vLLM can better serve real production scale deployments. So yeah, we're experts in that. So, yeah, we wanted to give a shout out to AI Bricks. If you're interested in deploying vLLM, it's a battle tested Kubernetes serving stack developed by ByteDance and used since this last year, I believe. And they wrote a nice blog and, of course, Project README, talking about what's in this production stack. And I think it should be useful and interesting to a lot of people that are trying to get to that next scale of vLLM deployment. Certainly it's an interesting and well presented project with many features that should hopefully give you pause and a better idea of what's needed to make a fault tolerant um, production ready inference system. Now, of course, we had 2 vLLM releases since the last office hours. So first we had 0.7.2. This was a pretty, I would say, accelerated one, as we wanted to get any DeepSeek improvements out as soon as possible. Of course, Qwen 2.5 VL was a really capable multimodal model that released that we wanted to support. And we also got this new transformers backend, which means now vLLM can increasingly be run with arbitrary Hugging Face models where we don't need to, create our own model definition specifically for vLLM. This does trade off a bit of performance. You're going to lose some performance by not having native vLLM integration, but obviously it gets you started with running models that you can otherwise run in vLLM, and gives us a nice stepping stone to support more models. Yeah, here in this release, like I mentioned, a big focus was more improvements to DeepSeek, and the main thing here was the initial enablement of MLA, which we'll get into detail on why this is such an important optimization, and various other optimizations. Yeah, I think that's the majority of the things in this release. And then we had sort of the much larger 0.7.3, where we had almost 100 contributors, I think in like less than 2 weeks. So it was a really great hectic time of getting a lot of work in. We had a lot of improvements to DeepSeek, so enabling the multi-token prediction modules, which now are sort of modules that are built into DeepSeek for essentially like free speculative decoding, which we'll explain a bit. Expanding support for AMD for DeepSeek, giving like more tunings, and also enabling MLA. And then also optimizations for the MLA support on Hopper, so enabling Flash Attention 3 to be used for MLA prefills, which greatly improves prefill and input token throughput. Various optimizations for preparing the experts or preparing expert selection for the MLA kernels that we have for DeepSeek. And then also expanding MLA to not just work with unquantized or FP8 quantization, but also work with AWQ and now GGUF and the many other different types of quantization. So you can still have compressed performant KV cache. with whatever quantization you want to use. And then, of course, there's been a lot of consistent work on the V1 engine. Hopefully, in this next release, you will see a lot of work being done on V1. But I think the main focus in this release was LoRa support, log prop support, various sampling parameter support, pipeline parallelism, adding many more metrics, so you can see the performance of the server, and yeah, some really exciting initial performant speculative decoding support with Ngram. So definitely check out some of those PRs if you're interested. Yeah, another big thing was we expanded support for some new quantization formats. So there's sort of a new definition for the GPTQ quantization from GPTQ model, which allows for a lot more flexible GPTQ quantization. Same thing with Unsloth. They unveiled a really cool dynamic bits and bytes quantization. So getting that support from them was great. Also some new models from IBM, the first geospatial model in vLLM, and also Mamba models, Mamba 2, Bomba model. Tyler worked directly on these, so excited to get more state space model support. And then Ultravox, the latest version of their model, of course. And then, yeah, more support for the Transformers backend, more support for the LMs as we try to improve the multimodal processing performance of more and more models. And then I think there's a bit more. Yeah. So adding a good bit more hardware support. The initial parts of NVIDIA's FP4 quantization got added. So we're well on our way to, Blackwell support for, NVIDIA B200 GPUs. And then also a good bit of work on AMD, enabling more types of FP8 and actually starting to bring AMD to V1. We're working quite a bit on this. We also brought TPU to V1. We're hoping to bring a lot more optimizations and more performance there for both AMD and TPU, as well as NVIDIA. And then, of course, some updates to AWS Neuron and Intel Gaudi. One thing that might be interesting to some people is I think Nick actually added this, but some features to make it easier to have front-end features to the vLLM engine. This made it sort of easier to implement sleep and wake commands, which are used for RLHF workflows, where you want to sort of suspend the memory usage of vLLM while you want to do some other things on the GPU. And we also added a sort of audio transcription endpoint support, so kind of mimicking the OpenAI API here. But this really makes it easy to use Whisper as an OpenAI style API with vLLM. Yeah, some performance enhancements, of course, as always, and some various integrations and bug fixes with structured output. And a really cool thing is vLLM v1 got integrated with the PyTorch open source benchmark database. So if you're interested in seeing more fine-grained, standardized benchmarks over a vLLM over time, check out that PR, and hopefully we'll share some better links with how you can track vLLM's performance in the PyTorch performance dashboard.
Hey, Michael, before you move on,
Yeah.
we're reaching our 100 participant capacity in Zoom. So if there's any internal Red Hat or Neural Magic people, there are live streams you can watch. I would really appreciate that. Thank you, guys.
Oh yeah, we are to cap. So definitely, if anyone can't join, share some of the live stream links. So yeah, without further ado, let's get into the DeepSeek updates, which we have a lot. So I think I'll hand it off to you, Rob, to kick us off.
Sure. So yeah, DeepSeek, it's been in the news. I don't know if you've heard about it. One thing about DeepSeek, in addition to being a really, really great model, and bringing a lot of new capability, through the reasoning capabilities that, have been added to R1, which has driven obviously a ton of interest in the model. It's also a very complex model, especially in comparison to the existing infrastructure. And, there's been a really awesome kind of technical reports that DeepSeek has launched about how they trained the model and some of the features that have been added to it. So examples of this include things like MLA, things like multi-token prediction, things like having 256 experts in their MLP layers, which is much, much bigger than, what we've seen from other models like Mixtral, which only has 8 experts. It's a 600 plus billion parameter model that's too big to fit even on a single H100 node, 8 by H100 node. And it was one of the first foundation models that's really been trained in block with FP8 quantization. And so it's a really, really complex model, which has been made for a very, very exciting set of weeks, for us as we try to ingest this model and bring in optimizations and to make all these faster since, before DeepSeek R1 came out, we had been spending a lot of our focus on llama style models and making those more efficient. And so as DeepSeek has brought in all of these new features, we've been working really hard to, make them all work performantly and take advantage of these optimizations. So it's been a very, very fun couple of weeks, and we'll have a couple more weeks of fun as we push forward and productionize and harden these features. And so, there's been a really cool chart that's been swinging around from Unsloth that's I have on the right-hand side, which, just shows the pace of development, over the course of the past month as we've integrated MLA, we've integrated things like torch.compile, we've integrated things like multi-token prediction, and just tracking the performance of various LLM serving frameworks, some of which leverage vLLM, and, how the performance in terms of number of tokens per second has been growing really, really fast. So we're really excited to kind of talk through, each one of these optimizations. So next slide. And, as Sasha mentioned, this really, really complex model, has, created a lot of opportunities for us to implement new optimizations. And concurrent with this, DeepSeek has been, having their open infra week over the course of the past week. We're currently on day 4. And what's been happening is DeepSeek has been releasing a series of inference kernels that, help to accelerate a lot of the features that they have been implementing. And so we'll cover each one of these optimizations like FlashMLA or DeepEP that have emerged, and we'll talk through our progress in integrating these in. And if you want to follow along to the work that we're doing, we have a GitHub project, which is listed below. And then we also have a Slack channel where we're discussing a lot of these optimizations that we're bringing in. And so this is how it's felt. I don't know if anyone is a football fan, but that's DK Metcalf chasing down Buda Baker after an interception. That's kind of what it's felt like over the past couple of weeks as we've been sweeping through and implementing a lot of these. So we'll go through kind of each one of these optimizations, discuss, what they are, why they matter, and then, the current state of them in vLLM and our plans to kind of finalize these features over the course of the next couple of weeks. So let's start off with MLA, and we can hand it over to Lucas.
Yeah, cool. Thanks. So this is going to be fairly high level, but we'll still be on for the question period. So if we have some more in-depth questions, we're happy to field those. But basically, the concept behind MLA is that instead of doing something like multi-head attention or group query attention, where group query attention tries to like compress or shrink the size of the KV cache by sharing key values across multiple query heads so that you're actually storing less data. DeepSeek took a slightly alternate approach where they actually took a standard kind of multi-head attention and they took all of the key value heads and they projected down into this latent space that can be much, much, much smaller. And then when you're actually doing inference, you project it back up and you just compute normal multi-head attention. They also, in the paper, described this matrix absorption path where you can actually compute directly on the latent space. And this can also help reduce like bandwidth bottlenecks. Because one of the issues with really long context inferencing is that if you're doing a decode and you have a very small query, then as you're loading the KVs in from like global memory, you can get bottlenecked on that bandwidth between global memory and your shared memory or register file. And so having these two different approaches that we can take to multi-latent attention is a really nice kind of feature because it allows us to optimize have pathways for compute bound cases and pathways for memory bound cases. But the most important thing is that it just dramatically shrinks the cache, like 10 times smaller. And this can like really up throughput cases because we can just batch much bigger. So if you want to go to the next slide. Yeah, so here we can see this kind of in full effect. So when we originally just in the 7.0, we with multi-head attention, the max tokens was about 67K. And that's now 650K. So this is like a dramatic increase in the amount of batching you can do, and your match back size for a 1,000 input, 7,000 output goes from 16 to 162. So this is really, I would say, primarily a throughput kind of optimization. We're hoping to kind of boost the decode throughput just based on the reduced global memory to shared memory transfers and seeing some speed up there. But there's still a lot of optimization work to go to get around that. It's like fairly complex pathways, which require a lot of small Python drops that we need to kind of slowly pick away at. Yeah, let's go to the next slide. And so this kind of just demonstrates that initially when we dropped MLA, the kernel was very, very slow. And there's lots of reasons for this. There's challenges around weird head dimensions. So in MLA, your Q and K head dimensions are different than your V head dimensions. A lot of attention kernels don't support this. So we're trying to bring that kind of support online, but it's taking time. And it is also a little bit more challenging than some of these smaller head dimensions. And so this just kind of shows that with these DeepSeek model, initially, these kernels were very, very slow. But over time, we're really improving them. So if you want to go to the next slide. Yeah, so here was just a bunch of different PRs that we did to kind of improve the end-to-end latency of MLA. And this work is still very, very much ongoing. So some examples here is like having FA3 for MLA. We did some cache alignment as well and shrunk the size of the cache. And then also chunk prefill. Chunk prefill has some unique challenges that are still being optimized, mainly around keeping the peak memory down. The challenge here is that when you up project the cache, you can create if you have very long contexts and you have to up project that full context, you can have a bit of an explosion of memory. So we have to take a slightly more complicated approach here where we end up chunking up the context and computing it incrementally, which still needs some work to kind of optimize. Yeah, and then V1 is a big one too. So we're still seeing a lot of CPU bottlenecks in V0. This is still very true for MLA. And so sometimes when we add MLA optimizations, we don't really see it in the end-to-ends because the CPU bottlenecks are still there. And this is somewhat apparent with the FlashMLA. So I guess we'll get to that in a bit. So maybe next slide. Yeah, so this now leads us to the FlashMLA, which is the first drop that was dropped by the DeepSeek open source week. And this was a kernel specifically for doing the matrix absorbed route, so larger head dim. And this is now merged, it's integrated, it's ready to go. And we are seeing a little bit of end-to-end speed up 10%, but we're seeing a lot more on the V1 implementations. And this kind of goes back to those CPU bottlenecks that we're still kind of battling with the complexity of the MLA attention scheme. But it was really awesome that they open sourced this. It's a nice kernel, and we were happy to get it in quickly. And so if you want to go to the next slide. So V1 support is in progress for MLA. So we landed V1 support with Triton MLA today, and V1 support with FlashMLA is on deck. And as we can see here, we can see the improvement by adding FlashMLA, or kernel improvements are showing up a lot nicer in V1, which is really, really nice. This, however, is for a very long context, and we are still seeing worse latency in V0 for V1 compared to V0 for very short contexts. So these are just some caveats. The optimization work is still ongoing, but I think we're like very happy with the progress that we've been making over the last couple of weeks. A lot of this enabled by DeepSeek open sourcing their kernels, and the and V1 just being less CPU overhead in general. Yes, and then on to MTP. And
let me dive into it. So, in particular, like, I think one important piece to remember with, these DeepSeek models is they do reasoning. And what this kind of means is the workload pattern that we see on the vLLM side tends to be very, very long generations, right? Because all those reasoning tokens get generated before the final output gets created. So, in the past, when we've kind of looked at a lot of benchmarking scenarios, we've often spent a lot of our time, thinking about shorter context kind of, models, because they don't have this similar kind of like long generation pattern. And MLA is a really important optimization for that type of workload, because as we generate longer and longer and longer, the KV cache gets bigger and bigger and bigger, and so there's a lot of pressure on the amount of GPU memory that we have, which can kind of limit the amount of batching that comes in. And so, MLA is obviously a great optimization, that DeepSeek has put in for, this specific type of workload that you're likely to see. But another example of a feature that DeepSeek has added to their models to improve reasoning workloads where you have, relatively small batch sizes, but really, really long generations, is speculative decoding. And I think many in this room may be familiar with speculative decoding, but speculative decoding is trying to take advantage of the fact that low batch size decode, which is the part of the model where we're generating the decode phase. If this has a low batch size on it, we're what's called memory bandwidth bound, meaning the amount of time that it takes to do a GEMM operation is bound by how long it takes to move the weights from DRAM into the on-chip memory, right, at a super high level. So we have a chart here that shows the teraflops per second that you're able to achieve as a function of the number of tokens in the batch. What we can see is that for low numbers of tokens, we're not able to kind of achieve that total flops, because we're in this kind of memory bound case. And so speculative decoding is an optimization that is specifically set up to turn a memory bound problem into a less memory bound problem. And basically, speculative decoding, the way that it was originally set up, is we would have a small draft model that would predict n tokens ahead, and the big model will, instead of predicting one token, will verify n tokens, which helps to expand the batch size. And if the acceptance rate is high enough, this extra work from generating the draft model is overcome by the fact that you have a bigger batch size, which gives you more throughput, right? That's the overall kind of conceptual idea behind why speculative decoding is something that's interesting. And speculative decoding is a useful optimization for generic model serving, but it's in particular a great optimization for something like DeepSeek, because DeepSeek is a reasoning model where we're going to be bound, but the batch sizes are going to be lower because we're doing really, really long generation, and because reasoning creates a really long decode phase that can actually be accelerated by the draft model. And so one of the really interesting features that's been happening in the open source ecosystem is there's been a series of methods that have been created over the course of the past several years where we expand beyond having a smaller draft model by adding additional projection heads to the model to predict multiple tokens at a time. So examples of this are techniques like Medusa, techniques like MLP Speculator, techniques like Eagle, that have emerged over the course of the past couple of years, or maybe I guess over the course of the past year or so, that are adding additional projection heads to the model to predict multiple tokens at a time during that forward pass. And so DeepSeek was natively trained with these multi-token prediction heads. It's an Eagle-like structure where there's multiple MTP modules that during the initial forward pass will predict multiple tokens at a time, and then in subsequent inference passes, we're verifying whether those forward projections were correct. And so this is a really nice feature that the model has, and it's specifically designed with kind of reasoning in mind. So if we can jump to the next slide, the folks at Meta implemented MTP over the course of the past couple of weeks. And, as expected, we've been seeing some nice speed ups from MTP in the in the low QPS kind of rates, when we're in that 1 to 10 kind of QPS rate, with some modest concurrency, we're able to see some nice speed ups in the 20% range end to end, which is a nice setup. But of course, speculative decoding is a technique that has trade-offs. So this is not a method that you would want to use in a offline batch kind of use case, because the overhead from the multi-token, you're already in a compute bound case. So this is a really nice optimization for someone who's trying to optimize for latency in a kind of serving environment. We were seeing around 80% acceptance rate of the tokens on shared GPT, which explains why these multiple token prediction heads are useful. And so I'm hopeful that this is a feature that all future models will be trained with. But it's really nice to kind of see. And so in terms of further optimizations, we can go to the next slide. The folks at CentML have added an Eagle style MTP, which builds upon the initial work that the Meta team did to implement this model inside of to implement this technique inside of vLLM, which is great. I also posted a blog that they posted on this as well in the top corner if anyone wants to take a look. So continuing to kind of enhance the methods. And then we're working very actively on spec decoding in vLLM v1. This is the key kind of remaining feature that we have left. Lily from the UC Berkeley team has been working really hard on this. We currently support n-gram spec decoding. We've been working on adding n-gram with rejection sampling, which is kind of the next component of this. And then, we'll immediately follow this up with MTP. So, if you want to look at a PR that got a lot of reviews on it, check out that 186 comments on the initial implementation of spec decoding. But so continuing to kind of push forward on this, and we'll hope to bring this into vLLM v1 relatively soon. All right. So that's MTP. The other big area of interest with this model is that it's very, very large. So there's over 750 billion parameters. Forget the exact 671 billion parameters. And additionally, this model is unique in the sense that it has many, many experts. So previous mixture of experts models that we've seen, like Mixtral, had something more like 8 experts. And so what this means is we have some more opportunities for parallelism that we haven't pursued in the past. And we've done an office hours session that covered, distributed inference. Murali from CentML came on and talked about this in the past. We've discussed tensor parallelism. We've discussed pipeline parallelism. And so feel free to check those out for more details on how tensor parallelism works and how pipeline parallelism works. We're going to talk about 2 new flavors of parallelism. One is called data parallelism, which is different from distributed data parallelism you might be familiar with training. And we'll talk through that. But in addition, expert parallelism. So just to get started, why does parallelism matter? When we're dealing with very large models that don't fit into a GPU, the parallelism and adding more GPUs into the inference request creates overhead. Because we have to now deal with synchronizing the GPUs across ranks. So even though your flops and memory bandwidth will increase by 2x or by, n every time you add a new GPU, you have to deal with the fact that you need to synchronize between the GPUs at various steps of the computation. And so whenever we're looking at a distributed setup, it's very important to get the parallelism right to drive the best performance. And so what tensor parallelism is, which is the kind of default way that we do parallelism inside of vLLM, is we take an individual weight and we shard the weight across GPUs. So if we have the WQ matrix, we're going to take a piece of WQ, put it on rank 0, a piece, put it on rank 1, ... And there's 2 different dimensions upon which we could parallelize. One is upon the columns and one is upon the rows. And we live in a very fortunate world where transformers are really specifically designed in a way that we can, do a column parallel multiplication followed by a row parallel multiplication with one all reduce to synchronize across the GPUs. And so as we think about a transformer block, we have, we have a cycle of attention layers and MLP layers over and over and over again. And so the way that vLLM is set up is that we have a column parallel matrix as the first part of each one of those blocks, followed by a row parallel matrix, followed by an all reduce. And this overall cycle will allow us to do one all reduce call to synchronize the ranks per block. And so each decoder layer is an attention followed by an MLP. This means that we can do 2 all reduces per layer. And this really, really minimizes the amount of synchronization that we need to do between the GPUs. But the challenges with this are when we deal with a very, very, very large model, we may not even be able to fit the model in one individual node. And then we're dealing with communication between multiple nodes. And so this introduces potential needs to do different parallelism. And for a model like DeepSeek, where we have 256 experts, if we shard each one of those experts over 8 GPUs, we start to get very, very, very skinny matrices, which can lead to underutilization of the tensor cores. And so both of these concerns create potential for doing different types of parallelism. So to the next slide. So one example, which has been supported in vLLM for a long time, is pipeline parallelism. This is really the recommended target if you're doing a multi-node setup, or one of the targets you should consider if you're doing a multi-node setup. And basically with tensor parallelism, what we do is we take the weights and shard each one of those weights. So if we have a model with 4 layers, half of each layer is going to be on GPU 0, half of each layer is going to be on GPU 1. With pipeline parallelism, what we do is we shard the model vertically. So layers 1 through, n over 2 will be on GPU 0, and then layers n over 2 plus 1 to n will be on, GPU 1. And the key challenge with pipeline parallelism is dealing with bubbles that will occur in the network, as we have, since per batch, only one of the GPUs can be active at a time. And so inside of vLLM, we have a way to create micro batches, which tries to, utilize both GPUs at once. Again, you should take a look at the vLLM previous office hours on distributed inference for more, details on pipeline parallelism. But this is a deployment mechanism that we can really use in a multi-node setup to deal with the fact that the interconnects between nodes are slower than within a single node. But let's hop on to the next set of stuff, which we'll talk about some of the new techniques. So for expert parallelism, this is a different way to shard an MOE model. As I kind of mentioned, when we're looking at DeepSeek, which has 256 experts, which is much, much more in comparison to a mixed-role model, we can start looking at expert parallelism. With expert parallelism, what we do is rather than sharding each expert across separate GPUs, what we do is we put specific experts on specific GPUs and instead route the individual tokens that are mapped to certain experts to the proper rank. And so the Berkeley team did a nice job of doing a first implementation of EP. And this is another technique that we can explore and are working on integrating into vLLM. Up to the next slide. And then beyond this, another dimension that we can explore is data parallelism. And this method is something that is very important when we're dealing with MLA. As Lucas talked about MLA up front, one of the things that we have to deal with is how do we shard attention? So when we look at like a GQA model, like a llama model, which has grouped query attention, what we can do is we can shard the Ks and Vs upon ranks. So the Ks and Vs are, the first 2 rows of each one of these charts on the right. But when we look at something like MLA, there's only one KV vector, right? Like this latent compressed KV state, there's only one of these, which means that we can't shard this across ranks, which means that in the initial implementations of MLA, we were repeating all of this computation across every rank because we needed to replicate the latent compressed KV across all of the ranks. And so when we talk about data parallelism in the context of the LLM, what we're really talking about is, enabling certain items of the batch to run on rank 0 for attention, and certain items of the batch to run on rank 1 for attention, such that we can not have to duplicate the KV cache and attention work across every rank as much as we can. And so, as you might kind of start to understand, as we start looking at something like expert parallelism and data parallelism, we need to introduce some new designs across the whole vLLM system, whether it's at the server level and the engine core level, all the way down to the collective ops that we're doing inside of the model. So I'll pass it off to, I think, Nick next to discuss, some of the changes that are being made to the, overall engine to, support these new methods.
Thanks, Rob. Yeah, so I'm going to just talk for a minute about how we are looking at sort of adjusting the existing vLLM architecture, and in particular the V1 architecture we're focused on for this, to support data parallelism quickly, so we can exploit it for the DeepSeek model and all of these changes. So this just sort of shows some of I think this diagram was actually put together by Cody from Anyscale, and but this was like just brainstorming how we can with minimum changes, what can we do to balance the requests between multiple engines now, where we have to load a copy of the model in each engine. And the first option would be to try and do it within the engine itself, and the middle one is sort of having a queue where we have separate schedulers. We sort of settled on the sort of completely separate engines. It actually fits nicely with the V1 design, where we decouple the API server and the front end processing in a separate process. We're using 0MQ to dispatch requests to a sort of core engine, which is a tight loop. So we avoid any CPU overhead from processing the front end, doing the sort of encoder input processing, the deserialization, that kind of stuff. So what we can nicely do here is sort of just replicate that core engine and have the API server client abstraction for that, understand the data parallel ranks and spawn multiple engine processes and balance the requests evenly between them. We're currently just we're doing a sort of basic load balancing, so we're trying to keep the number of requests even. Later, we might want to look at doing balancing that's a sort of prefix aware, so we can maximize the prefix caching that will happen in each sort of independently in each of the engines, and maximize minimize the duplication of the KV cache between the engines, because they have their own KV cache. Yeah, so that's basically what we're doing for the server. Kai Chow from UC Berkeley team had put together a sort of offline version of this, where it's sort of a full single process multi-data approach. So that's already working, and then I'm working on the server implementation. Maybe you could jump to the next chart. So yeah, this is just showing the PL. So the one on the left, Kai Chow had added a new group, a sort of torch distributed group for the data parallel coordination that needs to happen. So one of the things we need to do is synchronize the forward passes across the engines, so that when the expert layer is done, right, the MOE layer, we can sort of distribute the tokens appropriately that are being shared across this sort of the orthogonal experts. And something that's needed for that is if one of the engines is idle and not processing any requests, we need to make sure that we do sort of dummy forward passes, so that they all sort of participate in those collectives in the MOE layer. So that's part of what, as well as the sort of load balancing of the requests, we need to make sure that we sort of keep track of when
there are no requests in flight for some of the engines, but are in others, and we sort of inject these dummy forward passes to sort of keep everything even. So the setting up the communication for this was this first PR on the left, and then adding the sort of data parallel into the async abstraction is the middle PR that I was doing. So we can just sort of, like, you launch vLLM with vLLM serve, and you can just say tensor parallel size equals 2 or something if you're running it on a node with 2 GPUs at least. Then you can do the same with data parallel and just sort of put dash data parallel equals 2, for example. And then the third PR, Tyler will talk a bit more about, but this is actually enabling the distribution of the tokens among the experts when all of the engines reach the MOE layers. So I'll think hand over to Tyler to talk a bit more about that.
Yeah, thanks, Dick. So yeah, I'm mostly focusing right now on modifying the model execution to work with data parallel plus expert parallel. So remember, we're basically in a scenario where we've created multiple engines. These are going to be, starting these in parallel. They'll have like different schedulers, etc. Mostly we did this for simplicity, and they'll operate on different requests during attention and work on completely separate data, so that we're not replicating the attention state across the various like tensor parallel ranks as we do right now on vLLM. But then for the MOE layers, they'll basically come together, work on those layers cooperatively in an expert parallel way, and then redistribute for the subsequent attention. So essentially what happens is, we're basically modifying the MOE layers. We've got a data parallel, basically like MPI communicator to, collect the activations together. So if you've got the input to this layer will basically be activations that are replicated across your tensor parallel group, but then we need to collect them across the data parallel group as well. Then we'll enter this fused MOE layer. And so that kind of collection will be via an all gather right now, or, via sort of like a multicast. And then, everybody, sort of like takes those tokens, operates on their own experts, and then everybody has sort of a partial accumulation or a partial result of the entire output activation, and these need to get summed up. So right now we're doing this via a reduce scatter among data parallel ranks, and then a all reduce via a across the data parallel ranks or the tensor parallel ranks. So this is sort of like suboptimal. And I think some people have asked about like, where do DeepGEMM and where do DeepEP fit in? And they really fit in like right here. So DeepEP is, they have these, they have a, what do they call them? They have this like dispatch and combine kernel. So dispatch will take the activations and then dispatch them to the correct expert based on, the experts that they map to, but based on the top KIDs. And then the combine kernel will combine them together. And these are sort of designed hand in hand to fit in with the decode based masked layout gems in their DeepGEMM kernels that they released a couple days ago. So first we're working on kind of getting this working via some like naive-ish, all gathers, all reduces, and reduce scatter operations. And then we'll work on, kind of like slotting in these new kernels from DeepSeek as well. I think, yeah, I think that's it for me. Rob?
I think it's back to Michael now. Sasha, what's the next one? Yeah.
Sure. Yeah. So yeah, another thing that we need to think about here is the block FP8 format that DeepSeek v3 and R1 were released in. It was, we can say released this way because they say they trained the model in this way, so like native FP8 quantization. But this is also the format that we use for inference. So we had to support this block quantization format. And, first I wanted to kind of cover like why this is like interesting and important as a quantization format. So kind of most commonly, we support either like per tensor or channel-wise quantization. We do also have like grouped quantization for like fine-grained quantization like in 4. But for FP8, we kind of really haven't gone beyond that. And so, the key way to think about this is per tensor means we have like one scale for, changing the dynamic range of all the weights and quantizing it down. And then channel wise is where we have like one scale per a row or a column. Here we're kind of using like 2D weight matrices as where each block is a different element. And then we have block quantization, where here I kind of have blocks of 2 by 2, and each color meaning it's a different scale that we're using. Now in the DeepSeek case, we obviously use 128 by 128, but this is representative. And so just having the block quantization means that we generally are able to keep better like local statistics for local groups of elements versus just making an assumption across an entire tensor or an entire row or column. This does give like more memory overhead because you have more scales generally than a column wise or certainly in a per tensor way. But this gives usually much better quantization accuracy. And it's also hardware friendly with the advent of tensor cores, because tensor cores work in, very fancy, but still 2D blocks. And 128 is a pretty good estimate for the kind of size of modern tensor cores. So how blocked FP8 is already supported in vLLM is we implemented Triton kernels originally for this. This was made on Christmas when DeepSeek v3 actually came out, so we could support the model very quickly. And then later, actually from Lucas, integrating Cutlass kernels that can also support this same format, and this offered much improvement in the performance, and this is basically our default path on Hopper GPUs. And of course, as mentioned before, in the third night of DeepSeek this week, they dropped DeepGEMM, which gives us dense and MOE, or called group gems, for block FP8 format. So we're already validating and benchmarking these against our current kernel implementations. So yeah, here's some PRs on the left, where I and Bill, also on our team, are working on testing the accuracy and validity of these. And on the right is sort of a table comparing various shapes from our Cutlass implementation against the DeepGEMM implementation and also our Triton implementation. So you can see, we're much faster than our Triton implementation in most cases. And with DeepGEMM, there's currently some, let's say, like very unstable behavior where, sometimes it's much slower, sometimes it's a little bit faster. So, we're currently debugging and ultimately trying to replicate, the results that DeepSeek claim with these kernels, and trying to stabilize these. So then we get on to the fourth night, DualPipe. Rob, I think you wanted to cover this.
Let's see. They finally gave us a break and released something related to training. So DualPipe is a very, very cool algorithm. I haven't looked into it in too much details due to it being training and our focus being on inference. But the overall gist is that it's employing a pipeline parallel algorithm in the training process, which helps to overlap some of the communication. So I don't know too much about DualPipe, but it did give us a nice chance to rest a bit. You can hit the next slide, Sasha. But there was one very, very cool piece that was released last night, in addition to some very cool profile data from the actual production systems that DeepSeek uses, which showed some of the overlapping that they're able to achieve from production traces. But in addition to this, they released a small library which is really, really targeted at super high uh, uh, you know scale deployments, which is taking advantage of the fact that when we look at experts, a mixture of experts models, certain experts can be more popular than other experts. And this puts more pressure on certain experts than on others. And so one idea that you can do is to have redundant experts for the most popular queries, for the most popular experts that are routed to. And especially in DeepSeek setup, which they talked about, their production cluster has 128 GPUs per decode node or per decode instance, where they're doing 128-way expert parallelism. This creates an opportunity where if expert number n is 5 times more popular than expert number 1, you might want 5 times 5 copies of expert n and have 5 different regions where that token could be routed to better unify the amount of computation that's being done. So this is a really, really cool library. I think that we definitely have our work cut out for us to implement this inside of vLLM, but it's something that we will consider doing after we kind of get through the set of items that we've listed so far. And the fifth night tonight, we're very excited to see the grand finale. It's been a very, very fun couple of weeks working on this stuff. And yeah, it's been a great community effort, across Neural Magic, now Red Hat, Berkeley team, the Meta team, and additionally, obviously, from some outside contributors like Sentinel and others. So we're really excited to keep pushing on DeepSeek, bring all these together, and release our best shot at this. The performance has been improving quite a bit over the course of the past couple of weeks, and we're excited to bring all these together. So yeah, I guess we can open it up for questions.
Yeah, that's basically it. We perfectly allocated the given time, but I think we can stay a little bit longer, and feel free to come off mute and ask questions directly as we go through chat. And do you have any information on your sparsification router algorithm for model generation? Not sure.
Thank you, Robert, for the question. So basically, this is a very like a rudimentary question that if I want to have my own custom specification, can I do that with the vLLM model? This is like a high level question even before I go and try to investigate.
Do you mean like for weights or like?
For weights or attention matrix, basically any kind of like a matrix reduction through the decode layers or any other kind of layers, where actually like in the basic level we could use any kind of like a matrix reduction technique as we have been using other kind of techniques. I'm just trying.
I mean, you can, there's like a base like linear class and we implement like a quant method, and this is where like all of the, like dozen plus quantization methods and vLLM, implement like a forward function essentially for, given some activations and of course the layer it's working on producing an output. So you could put anything in a new like quantization backend, even if it's sparsity.
Okay, so that is helpful. So basically, I am actually local in the area. I live in Westford, so definitely when I heard about from, I think there was a jam in a couple of weeks, so I would like to stop by and probably get a little bit more information. Thank you.
Sure, of course. Anyone else?
Yeah, I just have a question on the reasoning tokens that you're observing in your benchmarks. For the same output sequence length, like how much more reasoning tokens are you observing, and how is the performance impacted?
I think like more what I was getting at is like I think it will vary per, query, of course. More what I was getting at when I was talking about reasoning is like the shape of like whenever we're doing an optimization in VLM or we're working on performance, like the shape of the input distribution and output distribution has a huge impact on the end-to-end latency that we'll see, as well as which optimizations make sense to apply, right? And so what I was getting at with like, there being a lot of reasoning tokens is when you have models that are generating thinking tokens, the workloads tend to have longer context, and Sasha, you're they tend to have longer context, and they tend to have more decoding, phase. Right? Like, and so that's why in a lot of the benchmarks we've been showing around DeepSeek and where we've been focusing more of our effort is on these scenarios where the inference generations are very long, and you're in this long context regime where things like attention and KV cache size really start to matter. As compared to, looking at more standard benchmarks where, maybe you have 1,000 input tokens, 100 output tokens, it's not going to be as, the workload will just respond differently. And so that's what I was getting at with, like why DeepSeek made some of these choices in their architecture. Like the reason, or I think one of the reasons why they're choosing MLA is because, the KV cache sizes are going to be so big. And why do they implement MTP? It's because, they're going to be doing all these generations and they need to keep the latency low. And the batch sizes will be relatively low. So that's kind of what I was getting at with those, as opposed to, us running a bunch of queries against DeepSeek and measuring how many tokens were being generated. But like also this contrasts with like a lot of other, test time scaling methods. Like we've seen, other methods that have been emerged where, maybe you're doing like a process reward model and you're generating hundreds of requests, and there's a, reward model that's deciding which one of those requests is doing well and then it's killing off all the other ones and, generating more from there. What you tend to see with a workload like that is much longer pre-fills. You're going to do a lot of KV cache hits. And so you're going to want to have a really good prefix caching implementation. That's going to be high batch size as opposed to like low batch size. And so things like, speculative decoding are not useful like in that kind of context. So that's more what I was getting at is the shape of the workload looks like this because the model will generate thinking tokens, in contrast to a lot of other workloads that we've seen so far. Does that make sense?
Yeah, thank you. So the thinking tokens are a black box here, right? We don't really know.
I mean, when you're working with DeepSeek, they're not a black box. Like you can see these models, you can see these tokens. They'll be generated, as usual. So as compared to a proprietary model, they might keep those thinking tokens behind the scenes. But when you're working with an open source model, like you can see what the reasoning tokens look like. Yeah.
Thank you.
Right. Any more?
Have you benchmarked the 3DAO's FlashMLA?
The flash attention MLA
Yeah,
implementation?
from 3DAOs, not from DeepSeek's.
We have not yet. It is
Okay.
on the to-do list.
Okay, thank you.
We're just trying to get we're trying to get FA3 with the different head dims for the prefill case, but we haven't benchmarked the decode case yet, but I think this is very interesting because it also lets us save a concat. So I'm quite excited about that. But yeah, it's on deck.
Thank you, Lucas. And can you go back to the slides that you compare the performance between sorry, the one that you compare? Yeah, this one.
Yeah.
So this is a block wise or group wise?
Yeah, this is block 128.
128 by 128, right?
Yeah, 128 by 128. Yeah.
Okay.
And then 1 by 128 on the activations. Because it's like per.
So sorry, 128 by 128, and the other one is 1 by 128. Is that?
Yeah, because it's like per token blocks. Yeah.
Token blocks. So it's like the group wise in the terminology.
Yeah, but just for the activations, right?
Just for the activation, yeah.
Yeah. So yeah, these are definitely work in progress. Don't look too closely.
Yeah, I know.
Like, as you can see, there's like very specific shapes where DeepGEMM like locks in and does really well, and then on other shapes it seems to fall apart. I don't know if this is because I'm on an H100 and they're on an H800, or this sort of takes debugging too.
Yeah, that will make difference. They use non-power to tile size.
Yeah.
So it will make difference on different hardware.
Yeah, but one thing that's clear is that it seems to be like particularly good at really large, really large M. It's able to get like more throughput. You can look at some of those, 4K M, and you can see it's about 20% faster than our Cutlass one. But our Cutlass implementation can also like see more tuning.
Yeah, we are working on that too. So we can talk about that. So we don't like to repeat the word.
The other thing is this is not on CUDA 12.8, which we think might be important.
Yeah, 12.9 will get the performance much better.
Okay. Yeah. Thank you.
And when you say it's the Cutlass version, is it in Cutlass repo or it's your own repo?
The Triton?
No, the Cutlass one.
Yeah, it's in our repo.
Yeah, it's repo, but hoping to replace it with the one that the PR that's up.
Oh, got it.
Yeah. But currently it's still the old one. We haven't touched it in a while.
Okay, thank you.
Okay, great. Well, if that's it, I think we can call it there. Hopefully you enjoyed the dump of information, and please ask us and keep us honest about DeepSeek optimizations as we continue to work on them. As always, contribute to vLLM, learn more about it, dig into the PRs, issues, and RFCs that we work on. We want to keep development open, and you expressing your opinions are the best way to keep us aligned. Come join the vLLM Slack and like talk to us directly. There's many special interest groups and feature channels to jump into specific topics. As mentioned at the beginning, the next meetup for vLLM is happening on the East Coast in Boston, come March 11th, if you're nearby. And as always, we're hiring vLLM engineers at Red Hat and Neural Magic. So if you want to work on this stuff, we're gladly hiring. So thank you from all of us, and have a great week. Let's see what we get tonight. Take care.